In the latest advisory window, the National Hurricane Center flagged the operational signal. Arthur was no longer a tropical cyclone, yet 5 to 10 inches of rain, with isolated totals near 20 inches, remained possible inland. One signal would be unusual. Several signals together are harder to dismiss. The storm had weakened on paper. Heavy rainfall was still spreading from the Gulf Coast into parts of the southeast. Flash flooding remained described by federal forecasters as dangerous to life-threatening, and the Weather Prediction Center was still tracking rainfall tied to Arthur's remnants after the tropical label had faded. That combination matters because the atmosphere does not stop moving water just because the storm loses its name. But that is not the most dangerous part. The headline is not only Arthur moving inland. The hidden number is how fast the rain falls before streets, drains, ditches, culverts, and low crossings can move it away. This is not just a weakening storm, this is a drainage system failure. So the question is no longer simply where Arthur goes next. The question is what happens when tropical rainfall reaches the road, the hospital, the ambulance route, the neighborhood drain, the power crew, the trapped driver, and the city built around older assumptions. Like, subscribe, and comment where you are watching from, because this map is not only showing a storm, it is showing where flood risk may appear first, but the map is only the surface. The next clue is inside the operations room. At the next advisory window, the National Hurricane Center did something that can sound reassuring if it is heard too quickly. It said Arthur was no longer a tropical cyclone. The structure that gives a storm its tropical identity had weakened. The wind field was no longer the clean, organized signal that defines the public imagination of a named storm. On paper, that looks like the moment when the threat starts to leave. But in an operations room, that is not the moment when the room relaxes. The same official message carried another signal. Arthur's remnants were still expected to produce heavy rain across the southeastern United States. The forecast still carried 5 to 10 inches of rain, with isolated amounts near 20 inches. The National Hurricane Center still described the flash flooding threat as dangerous to life-threatening. So the first light on the dashboard was not the storm name, it was water. That matters because emergency systems do not respond to names, they respond to load. A tropical storm can lose its form while the moisture field continues inland. A center can weaken while rain bands keep feeding. A wind advisory can fade while a flood warning becomes more important. To a person watching a television map, the story may appear to be moving from red to yellow, from storm to remnant, from emergency to cleanup. But to forecasters, dispatchers, drainage crews, road departments, and emergency managers, the event is not over when the tropical label disappears. It changes departments. At one desk, the National Hurricane Center tracks the remaining low and the end of tropical cyclone status. At another desk, the Weather Prediction Center tracks the rain shield, the placement of heaviest bands, and the areas where rainfall rates can outrun the ground. At local National Weather Service offices, meteorologists look at radar returns county by county, not because the storm is dramatic, but because the next warning may depend on a band of rain sitting over one town for too long. That is the first operational truth of Arthur moving inland. The danger is being handed from one kind of system to another. It begins with the advisory. The official language is careful. Arthur is no longer a tropical cyclone. The remnants are moving inland. Heavy rainfall remains possible. Flash flooding may be dangerous to life-threatening. Those words are not written for drama. They are written because the atmosphere still has work to do, and the ground still has to receive it. Then the map changes. The cone matters less. The rainfall forecast matters more. Instead of asking where the center will cross, the question becomes where the rain bands will train, where soils are already wet, where urban drainage is undersized, where low roads collect water, where creeks rise quickly, and where people will be traveling when the heaviest burst arrives. That is why the Weather Prediction Center stays in the story after the hurricane advisory begins to sound quieter. Its role is not to keep the name alive. Its role is to follow the water. By the next set of updates, the Weather Prediction Center was already seeing the second signal. Heavy rain associated with Arthur's remnants was spreading across parts of Alabama and Georgia. Radar was showing showers and thunderstorms wrapped into the system. The rainfall threat was no longer only a coastal concern. It was moving across inland counties where the storm surge map was irrelevant, but the flash flood map was not. On their own, these signals could be treated separately: a weakened storm, a rainfall forecast, a flood watch, a radar band, a local warning. Together, They describe one larger configuration, a storm losing wind strength while the water risk spreads inland. That is the abnormal pattern. Not because tropical systems have never done this before, they have. The abnormal part is how easy it is for public attention to move in the opposite direction from the real risk. The name gets weaker, the hazard gets less cinematic, the center becomes harder to track, the win number drops. People hear the word remnants and think the event has entered its harmless stage. But remnants can be efficient rain machines. Inside an operations room, the first screen is the official forecast. The second screen is radar. The third is rainfall over the last 1, 3, 6, and 12 hours. The fourth is flash flood guidance, which asks a simple operational question. How much rain would it take, over a certain amount of time, to create flooding in this basin? The fifth is the road network. The sixth is the call log, and somewhere between those screens, weather becomes consequences. A band of heavy rain over rural ground may produce runoff into creeks and low crossings. The same band over a city can overwhelm storm drains faster than crews can clear them. The same band over a highway during commute hours can turn an underpass into a trap. The same band over a hospital district can slow ambulances and staff changes. The same band over a power crew staging area can delay repair work, even if the wind is no longer the headline. This is why Arthur is not only a meteorological event, it is an operational test. The first question is who is warning. The National Hurricane Center gives the tropical signal. It tells the public that Arthur has weakened, that the system is inland, and that heavy rainfall remains the main concern. The Weather Prediction Center gives the rainfall and excessive rain signal. It focuses on where the atmosphere is likely to put water on the ground faster than the ground can absorb or remove it. Local National Weather Service offices translate that national picture into county warnings, city timing, river statements, and road level concerns. Emergency management agencies watch all of it because they are not only preparing for water, they are preparing for people interacting with water. That interaction is where flash flooding becomes deadly. Most people do not meet flash flooding at a river gauge. They meet it at a familiar road that looks almost normal until it does not. They meet it when a ditch has become a current. They meet it when a small creek backs up into a low crossing. They meet it when storm drains stop swallowing the rain and the street begins to store it. They meet it at night in poor visibility, with headlights reflecting off a surface that hides depth. The dashboard sees that before the driver does. A flood watch means conditions are favorable. A flash flood warning means flooding is occurring or is imminent. A flood warning can mean water is already affecting specific rivers, roads, or communities. These are not decorative colors on a map. They are different stages of system stress. For Arthur, the system stress is not located in one clean point. It stretches across a region, along the Texas coast and into Louisiana. The early concern is tropical rainfall over low-lying areas and saturated ground. Farther east, Mississippi and Alabama begin to watch bands of rain that may organize and repeat. In western Georgia, the concern becomes how quickly rainfall rates build over towns, small basins, and transportation corridors. Across the Florida Panhandle, the issue is not only what falls from the sky, but how fast water can move through flat terrain, ditches, road shoulders, and drainage canals. Each place sees the same general event, but each place receives it through different weak points. That is what makes the day unusual. Not the existence of rain, not even the existence of a weakening tropical system. The unusual configuration is the mismatch between the public headline and the operational hazard. The public headline says weakening storm, the operational hazard says inland water load. The public headline follows the center. The operational hazard follows the rain bands. The public headline fades when the name fades. The operational hazard may peak after that. The map shows Arthur moving inland, but the system is failing at the places where water is supposed to disappear. A storm drain is supposed to take street water underground. A culvert is supposed to move water under a road. A ditch is supposed to hold flow beside the pavement. A pump station is supposed to move water out of low ground. A low bridge is supposed to remain passable unless the stream rises beyond its expected range. Each piece is small enough to be invisible on a national forecast map, but when the rain rate climbs, those small pieces become the event. This is where the Weather Prediction Center's role becomes central. It does not need the storm to look impressive on satellite for the threat to be serious. It needs to know how much moisture is available, how unstable the air is, how slow the rain bands move. whether new storms form over the same locations, and whether the ground below can handle more water. When those ingredients line up, rainfall can become concentrated enough to cause flash flooding even while the wind threat is no longer dominant. That is the hidden transfer. Arthur is moving from wind language into water language. In wind language, people ask about maximum sustained winds, gusts, power outages, falling trees, and structural damage. In water language, people ask about rainfall rates, drainage capacity, road closure points, small stream response, flooded basements, stalled vehicles, and rescue access. Both languages describe risk, but they do not move on the same clock. Wind often announces itself. Rain accumulation can disguise itself until the system has already lost margin. A road can remain open at the start of an hour and become impassable before the next warning is fully absorbed by the public. A creek can rise after the heaviest rain has already moved on. A neighborhood can flood not because a river has overtopped, but because local drainage cannot move the water fast enough. A hospital can remain powered and structurally intact, yet still become harder to reach because the surrounding streets are flooded. A fire station can be ready and still lose minutes because the direct route is blocked. Those minutes are part of the hazard. This is what the operations room sees that a simple storm track does not. It sees time as a resource. Time for a warning to reach a phone. Time for a driver to turn around. Time for a drainage crew to clear an inlet. Time for police to block a low road. Time for a family to move a car out of a flood-prone spot. Time for emergency services to reposition before the water cuts off a route. Flash flooding compresses that time. That is why one weakening storm can still create a serious emergency. The meteorology is no longer only about Arthur's center. It is about the speed at which water enters human systems. A forecast of several inches over a broad area is concerning. A burst of rain over one basin is more dangerous. Repeated bursts over the same corridor are more dangerous still. And if those bursts arrive where pavement, roofs, compacted soil, and clogged drainage concentrate runoff, the hazard becomes urban before it becomes regional. The city does not need a hurricane eye to flood. It needs water faster than its exits. That is the operational meaning of the day. Forecasters are not only watching a storm weaken, they are watching a region absorb water. Emergency managers are not only waiting for the center to pass, they are watching for the first road closures. Drainage crews are not only reacting to complaints, they are trying to keep small openings from becoming system failures. Hospitals are not only watching the weather, they are watching access. Drivers are not only driving through rain, they are entering a moving hydraulic system without seeing its full shape. This is not just a weakening storm. This is a drainage system failure beginning as an official warning and ending as decisions on pavement. The next important number is not the name of the storm, and it is not the wind speed left inside the remnants. It is the amount of rain the system can put down before the ground, the drains, and the roads run out of time. And that number changes everything. The number that changes Arthur is not the wind speed. By the time Arthur moves inland, the wind number has already lost much of its power to hold public attention. The storm no longer looks like the kind of threat people are trained to watch. There is no dramatic eye on satellite. There is no clean circle of violence moving toward a coastline. There is no simple image of landfall that tells everyone when the danger begins and when it ends. But the rainfall number is still there. According to the National Hurricane Center, Arthur's remnants could produce 5 to 10 inches of rain, with isolated totals near 20 inches. That is the headline number. It does not sound as cinematic as a major hurricane wind speed. It does not create the same instinctive reaction as a category. But in a flood emergency, that number can matter more than the name of the storm. 5 inches is not just 5 inches. 5 inches is about 127 millimeters of water falling onto roofs, parking lots, fields, road shoulders, sidewalks, ditches, and neighborhood drains. 10 inches is about 254 millimeters. 20 inches is about 508 millimeters. Spread gently over a long period, water can sometimes be absorbed, routed, stored, and released. But dropped across vulnerable ground in bursts, that same water becomes a force moving through the built environment. The number is not just rainfall, it is the drainage system being asked to work outside the calm conditions it was built around. That is why the forecast is not a decoration on a weather map. It is a workload estimate. Imagine a single neighborhood block. Every roof becomes a collector. Every driveway becomes a channel. Every parking lot becomes a sheet of runoff. Every curb becomes a shallow river guide. Every storm drain becomes a small opening responsible for removing water from a surface that was never meant to hold it for long. In ordinary rain, these pieces are invisible because they work quietly. Water falls, runs to the edge of the street, enters a drain, disappears underground, and the road keeps functioning. But 5 to 10 inches changes the demand. The street is no longer just a street. It becomes temporary storage. The curb is no longer just a curb. It becomes a boundary for moving water. The storm drain is no longer a background detail. It becomes the difference between a passable road and a flooded intersection. A ditch is no longer a strip of grass beside pavement. It becomes part of a regional water system under sudden pressure. That is the first reason the headline number matters. The second reason is location. The same amount of rain does not mean the same thing everywhere. 5 inches over dry, open ground can be serious. 5 inches over saturated soil can be dangerous. 5 inches over a paved urban basin can become flash flooding quickly. 5 inches over steep terrain can rush into creeks. 5 inches over flat coastal plain can linger because the water has nowhere fast to go. 5 inches over a drainage network already carrying water from earlier storms can remove the remaining margin. So when federal forecasters describe rainfall from Arthur across parts of the southeast, the real question is not only how much falls, it is where the water lands and what it lands on. A highway interchange does not absorb rain like a field. A shopping centre does not absorb rain like a forest. A neighbourhood of compacted lawns, concrete driveways, and narrow drainage channels does not receive rain the way a natural wetland does. The built environment has hard surfaces. Hard surfaces turn rainfall into runoff faster. Runoff looks for the lowest path. The lowest path is often the road. That is why a forecast of 5 to 10 inches must be translated into human language. It means the water on the map is moving toward the morning commute. It is moving toward delivery routes. It is moving toward school bus decisions. It is moving towards small bridges, frontage roads, rural crossings, underpasses, apartment parking lots, and hospital access roads. It is moving toward places that are ordinary until the hour when water begins to collect. A rainfall forecast is a pressure forecast for everyday life. The National Hurricane Center's number is also important because it separates Arthur's visible weakness from Arthur's remaining capacity. A storm can weaken in wind and still carry an enormous amount of tropical moisture. The public tends to connect danger with structure. If the storm looks less organized, it feels less dangerous. But water does not need a perfectly organized storm to become destructive. It needs moisture, lift, time, and a place where the ground cannot keep up. Arthur still had the water part of the equation. That is the part many people miss. When a storm is offshore, people often imagine the danger coming from the center. They picture a track line. They picture a rival. They picture the point of landfall. But inland flooding can separate from that mental picture. The heaviest rain does not always fall at the center. Rain bands can sit away from it. Moisture can be pulled into zones of lift far from the place people are watching. The remnants can interact with fronts, terrain, daytime heating, or local boundaries. The map becomes less like a target and more like a network. The storm track tells one story. The rainfall field tells another. For Arthur, the rainfall field is the story. 5 to 10 inches is enough to change the meaning of time. If a road department has a full day to prepare for gradual river flooding, it can place barricades, message boards, and crews in known low spots. If several inches arrive in a short window, the system has less time to react. Dispatchers receive calls before maps fully update. Drivers enter water before warnings feel personal. Police may have to close roads after the first vehicles are already stuck. Fire rescue may be asked to enter water while the rain is still falling. A number on a forecast becomes minutes lost in the field. It also changes the meaning of distance. A person may think they are safe because they are far from the coast. They may not feel connected to Arthur because there is no storm surge in their county and no hurricane wind in their forecast. But inland flooding does not need the coast. It needs drainage pathways. A creek behind a neighborhood, a culvert under a road, a low spot near an industrial park, a small stream crossing used by commuters every day, a flood-prone intersection that fills whenever the rain becomes too intense. The coast is not the only place where tropical systems leave damage. Inland water can be quieter at first. That is part of the danger. Wind announces itself with noise. Rainfall accumulation can build behind the scenes. The first hour may look like ordinary heavy rain. The second hour may look inconvenient. Then a drain clogs, a ditch fills, a creek rises, a low road disappears under brown water. The danger becomes obvious only after the system has already lost capacity. This is why the number cannot be heard casually. 5 inches may sound manageable to someone who has seen heavy rain before. 10 inches may sound like a lot, but still abstract. 20 inches may sound extreme, but isolated. Yet each of these numbers has a physical meaning. 1 inch of rain over 1 acre is more than 27,000 gallons of water. 5 inches over that same acre is more than 135,000 gallons. 10 inches is more than 270,000 gallons. And when that water falls over many acres of roads, rooftops, and parking lots, the scale becomes difficult to imagine. The city does not receive rainfall as a single number. It receives it as millions of small flows arriving at the same time. Some flows enter drains, some miss drains, some carry leaves, branches, trash, and sediment. Some back up at narrow openings, some race down slopes, some pool in flat areas. Some enter yards and crawl spaces, some push against doors, some fill the lowest part of a roadway, some lift vehicles just enough to reduce control, some hide the pavement edge, some erase the boundary between road and ditch. This is the translation of 5 to 10 inches. It is not a weather statistic, it is a rearrangement of the ground. The number also matters because flash flooding is not only about total water, it is about surprise. The word flash means the system changes faster than people expect. The familiar landscape fails its familiar role. A road that usually carries people begins carrying water. A ditch that usually sits beside the road begins feeding water across it. A creek that usually stays in its banks becomes a moving hazard. A parking lot that usually drains becomes a basin. The ordinary environment becomes operationally hostile. And it can happen while the storm itself sounds weaker. That is the core contradiction of Arthur moving inland. The storm is losing identity. The water is gaining pathways. This is not just a weakening storm. This is a drainage system failure. When the National Hurricane Center says 5 to 10 inches with isolated totals near 20 inches, the statement is not simply about how wet the region may become. It is about how many systems may be asked to operate near or beyond their margins. Stormwater systems, road networks, emergency response, hospitals, utility crews, local governments, families trying to get home, workers trying to reach night shifts, drivers deciding whether a shallow-looking crossing is safe. The rainfall number enters all of them. It enters the hospital when staff cannot arrive on time because the access road floods. It enters the power system when repair trucks must detour around water-covered streets. It enters the grocery supply chain when delivery routes slow. It enters the school system when buses cannot safely cross low roads. It enters household economics when a car stalls in water and the repair bill arrives weeks after the storm is gone. It enters public safety when rescue teams must spend time on preventable vehicle water rescues instead of other emergencies. That is the difference between weather and load. Weather is what falls. Load is what the system has to carry. Arthur's rainfall forecast is a load forecast. The strongest part of this number is that it appears after the emotional peak of the storm may already be over. People may already be downgrading the event in their minds. The name may feel less urgent. The wind may feel less threatening. The television graphic may look less alarming. But the rainfall number says the event still has a way to reach people. It reaches them through the ground. That is why the forecast has to be read from the bottom up. Start not with the sky, but with the lowest point in a neighborhood, the underpass, the culvert, the ditch line, the creek bend, the parking lot corner, the storm drain covered by leaves, the rural road that dips between two fields, the apartment complex entrance that always ponds first, the bridge approach that disappears when water backs up. Those places are not footnotes. In a flash flood setup, they are the front line. 5 to 10 inches finds the front line. Near 20 inches can overwhelm it. But even now, the headline number is still not the full story. Total rainfall tells us how much water may fall. It does not tell us how violently that water arrives. It does not tell us whether the storm gives the drainage system 12 hours to work or 1 brutal hour to fail. It does not tell us whether the rain is steady, broken, trained, repeated, or concentrated over the same vulnerable basin. That is why the next number is more dangerous. The total makes the forecast feel large. The rate makes it immediate. The total tells the region to pay attention. The rate tells a driver whether a road can disappear before the next mile. Arthur's rainfall forecast is the first warning, but the hidden number is inside the hour. The rainfall total tells you how much water may fall. The rainfall rate tells you how fast the system can fail. That is the hidden number inside Arthur's warning. The public headline says 5 to 10 inches, with isolated totals near 20 inches. That is enough to make anyone pay attention. But flash flooding does not wait for the final storm total to be measured. It does not wait for the rain gauge to finish the day. It does not need the entire forecast to verify across a whole region before it starts damaging one road, one neighborhood, one vehicle, or one rescue route. Flash flooding is written inside the hour, according to the Weather Prediction Center. Rain bands tied to Arthur's remnants were capable of producing rainfall rates around 1 to 2 inches per hour in parts of the southeast. That sounds smaller than the total. It is not. 1 inch in an hour is not gentle rain. 2 inches in an hour is not just heavy rain. In the wrong place, over pavement, over saturated ground, over a low crossing, or over a drainage system already carrying water, it can become the difference between a wet road and a road that stops being a road. The visible number makes the headline. The hidden number writes the damage. A total of 10 inches over a long stretch of time gives the system chances to breathe. Water falls, drains work, ditches carry flow, creeks rise and then move water downstream. Crews may have time to place barricades. Drivers may have time to change routes. The warning may have time to become behavior, but 10 inches is not always delivered like that. If several inches fall in a short burst, the system loses its spacing. The water arrives before the exits can clear. The drain at the curb may still be open, but it can only swallow so much. The ditch may still be in place, but it can only carry so much. The culvert under the road may still function, but if water reaches it faster than it can pass through, the upstream side begins to back up. The underpass may be designed to shed water, but if the pump or drain cannot keep pace, the lowest pavement becomes a basin. The total says how much water is in the storm. The rate says whether the street has time. This is the part of a tropical rain event that is hard to communicate on a simple map. A map can shade a region for heavy rainfall. It can draw a risk area. It can show a storm track. It can show counties under alerts. But the most dangerous part may be a narrow band that parks over one community for 45 minutes. It may be a repeating line of storms crossing the same drainage basin. It may be a burst of rain that falls while people are driving home, when roads are full and visibility is poor. The atmosphere can make the hazard narrow. The consequences can make it wide. A 1 inch per hour rainfall rate over a field is one kind of problem. A 1 inch per hour rainfall rate over a city is another. A 2 inch per hour rainfall rate over a neighborhood with clogged drains is different again. Add darkness, traffic, debris, saturated soil, and a low road, and the same number becomes a survival decision. That is why the hidden number changes the meaning of Arthur. Arthur is not only carrying water inland, Arthur is carrying water in bursts. It is not only a question of how much rain falls across the southeast, it is a question of where the heaviest hour lands. It is a question of whether that hour lands over a highway interchange, a small creek basin, an apartment complex, a hospital access road, a rural low-water crossing, or a neighborhood where storm drains already struggle during ordinary downpours. The storm is weakening, the hour is not. Rainfall rate is the speed of pressure on the ground. When the rate is low, the ground and drainage system can sometimes negotiate with the storm. Water enters soil, water moves along gutters, water passes through culverts, water enters storm sewers. The system may be stressed, but it still has a sequence. The rain arrives, the surface responds, the drains remove, the channels carry, the rivers rise. When the rate is high, that sequence collapses. Rain hits roofs and immediately becomes roof runoff. It pours into gutters and downspouts. It hits driveways and runs into the street. It hits parking lots and moves as a sheet. It hits compacted lawns and slides toward the lowest point. It reaches the curb before the storm drain can clear the last wave. It piles against leaves, branches, trash, and sediment. It finds every dip in the pavement. It fills the low side of the road. It spreads across lanes. It hides markings. It hides the edge. By the time a driver sees standing water, the failure has already begun upstream. This is why the phrase flash flood is not just a warning label. It is a timing diagnosis. It means the system may change faster than normal decision-making, faster than a driver expects, faster than a road crew can reach every flooded spot, faster than a family can move a vehicle from a low apartment lot, faster than a dispatcher can describe every closure, faster than a county map can show what the next road looks like. The danger is not only water depth, it is water speed, water surprise, and water arriving at the wrong part of the system at the wrong hour. A shallow-looking sheet of water can carry a current. A road underwater can hide a washed-out shoulder. A culvert can be overwhelmed beneath the surface while the pavement still appears mostly intact. A ditch can look like a puddle until the front wheels drop off the edge. At night, headlights reflect off the water and flatten depth. In heavy rain, the windshield becomes a filter. The driver sees surface, not force. That is where the hidden number reaches a human being. The forecast says 1 to 2 inches per hour. The driver experiences that as disappearing lane lines. The road department experiences it as multiple calls at once. The emergency manager experiences it as scattered incidents becoming a pattern. The hospital experiences it as staff delayed by flooded access roads. The power crew experiences it as a repair route that is technically open on the map, but impossible in the field. The dispatcher experiences it as minutes. Those minutes matter. 1 heavy hour can change the order of a night. Before that hour, people may still be going to work, stopping for fuel, picking up children, delivering food, or checking on relatives. During that hour, the same road network begins to sort people by elevation. Those on higher ground may see only heavy rain. Those near low crossings may meet water moving across pavement. Those near creeks may hear alerts after the channel has already started rising. Those in cars may have the least information at the exact moment they need it most. The body does not experience rainfall rate as data, it experiences it as urgency. And that urgency is not evenly distributed. A person with a flexible schedule can wait. A person on an hourly job may feel pressure to drive. A nurse finishing a shift may need to get home before the next shift begins. A caregiver may need to reach a parent. A delivery driver may be following a route set before the heaviest rain formed. A family in a low-lying apartment may not know whether the water outside the door is still only street flooding or the beginning of something worse. The rain rate enters their choices before it enters the official damage report. This is where Arthur becomes more than a storm remnant. It becomes a test of how quickly official information can become local behavior. A flash flood warning may be issued. Phones may sound. Weather radio may interrupt. Local officials may post alerts. But water does not wait for perfect comprehension. It is already moving through gutters, yards, roads, channels, and culverts. It is already testing small openings. It is already choosing the lowest path. That path can be brutal because it is ordinary. The flooded location is often not dramatic from above. It may be the same underpass that collects water every year, the same road beside a creek, the same neighborhood entrance where leaves gather, the same construction zone where drainage has been temporarily altered, the same rural crossing without enough lighting, the same commercial strip where parking lots drain toward the road. Flash flooding often begins where people have driven many times before. Familiarity becomes part of the trap. If the road was passable last storm, a driver may expect it to be passable this time. If the water looked shallow before, they may think it is shallow now. If the storm has weakened, they may assume the danger has weakened too. But rainfall rate changes the comparison. A weaker storm with a stronger rain burst can create a worse road condition than a stronger storm whose heaviest rain missed that basin. The headline is Arthur moving inland. The real story is the rain arriving too fast. That is why forecasters focus not only on the total, but on the atmosphere's ability to produce efficient rainfall. Tropical air can hold deep moisture. Warm cloud processes can convert that moisture into rain efficiently. If air keeps rising along a boundary, storms can keep forming. If those storms move over the same corridor, rainfall repeats. The sky becomes a conveyor. The ground becomes the receiving dock. The problem is not just how much moisture exists, it is how quickly the conveyor unloads it. When that unloading happens over a vulnerable basin, flash flooding does not need a large river. It starts small. A curb lane fills. A storm drain gurgles. A ditch goes from wet grass to moving brown water. A culvert begins backing water onto the road. A vehicle slows, then stops. Another vehicle tries to pass. Someone turns around, someone else does not. A call reaches dispatch. A road crew is sent. A barricade is requested. The rain continues. A second road floods. A third call comes in. The event expands from a rainfall rate into a public safety problem. The hidden number has become workload. This is not just a weakening storm. This is a drainage system failure. And the failure does not have to be total to matter. The whole city does not need to flood. One blocked underpass can reroute emergency traffic. One flooded hospital access road can delay care. One washed-out shoulder can trap a vehicle. One overwhelmed culvert can cut off a rural route. One cluster of water rescues can occupy crews while other emergencies continue. 1 hour of extreme rainfall can create problems that take days to unwind. That is why the safest interpretation of Arthur is not to ask whether the storm still looks impressive. It is to ask whether the water is arriving faster than the system can pass it along. The storm name fades from the top line. The rain rate remains inside the warning. The public sees weakening. The drainage system receives load. The forecast shows weather. The road receives water. But to understand why the rain can arrive that way, the story has to move upward first. The hidden hour begins below your tires, but its mechanism begins in the atmosphere. The hidden hour begins in the atmosphere. Before the water reaches a curb, before it fills a ditch, before it enters a culvert, before a driver sees headlights reflecting off a flooded lane, Arthur's inland flood risk begins as a moisture engine. The storm weakens as a tropical cyclone, but the moisture it helped pull north does not disappear when the label changes. It remains in the air, waiting for lift, waiting for boundaries, waiting for a place where clouds can turn stored water into rainfall faster than the ground can receive it. That is the mechanism. Tropical moisture moves inland. Rain bands form and reform. Some of them slow down. Some of them pass over the same corridor more than once. The atmosphere keeps feeding them with humid air. The ground below keeps losing capacity. At first, it looks like weather. Then it becomes hydrology. Then it becomes transportation. Then it becomes rescue. The mechanism begins above the Gulf. Warm water and tropical air create a deep reservoir of moisture. In simple terms, the air is carrying more water vapor than an ordinary air mass over the same region. Meteorologists often describe this with a measure called precipitable water. That does not mean water is already falling. It means the column of air above a location contains a certain depth of water vapor that could become rain if the atmosphere converts it efficiently. According to the Weather Prediction Center, the environment around Arthur's remnants included very high tropical moisture, with precipitable water values above 2 inches in some areas. 2 inches of precipitable water does not mean every place gets 2 inches of rain. It means the atmosphere is loaded. A loaded atmosphere can rain hard when the right trigger appears. The trigger can be a surface boundary. It can be convergence, where air near the ground comes together and is forced upward. It can be daytime heating, adding instability. It can be terrain. It can be the circulation around the remnant low. It can be a front or an old outflow boundary left by previous storms. The exact trigger matters to forecasters, but the basic process is simple. Air rises, rising air cools, moisture condenses, clouds deepen, rain falls. In a dry environment, that process may produce scattered showers. In a tropical environment, it can produce efficient rainfall. Efficient rainfall means the cloud does not waste much time or energy on ice processes high in the atmosphere. Warm cloud layers can allow droplets to collide, grow, and fall as heavy rain. The storm may not look violent in the same way a severe thunderstorm does, but it can pour water with astonishing speed. The sky becomes less like a set of isolated storms and more like a conveyor belt. That conveyor belt is the key. If the belt moves steadily, the rain spreads over a wider area. Still serious, but sometimes manageable. If the belt slows, bends, or repeats over the same place, the hazard changes. One shower passes, then another forms upstream and follows the same path, then another. This is called training, because the cells move like train cars along a track. Each individual car may pass, but the track keeps delivering more. Training rain bands are dangerous because they attack time. They do not only increase the total, they compress the delivery. A basin does not care that the rainfall came from 3 separate cells instead of one long storm. A storm drain does not care whether the water arrived from a named storm, a remnant low, or a boundary interacting with tropical moisture. A low road does not care what the satellite image looks like. It only receives water. That is why Arthur's weakening is not the end of the mechanism. The storm can lose tropical structure while still helping organize moisture. It can become post-tropical or remnant in the official record while the rainfall process continues. The wind field can relax while the rain shield remains productive. The center can become less important while the bands around it become more important. In this phase, the threat moves from a cyclone story into a water routing story. The mechanism begins above the Gulf, but it does not end in the sky. It moves into the surface. Rain first hits roofs. On a house, an apartment building, a store, or a hospital, the roof is a collector. A roof does not absorb water, it sheds it. Water moves toward gutters, downspouts, edges, walls, patios, alleys, and parking lots. Each roof is small by itself. Across a town, thousands of roofs become part of the drainage load. Then the rain hits pavement. Pavement is another collector. Highways, driveways, sidewalks, warehouse lots, gas stations, school parking areas, and strip mall surfaces all turn rainfall into runoff. The water does not soak in. It spreads, gathers, accelerates, and moves toward the lowest available path. On a dry day, pavement is transportation. In a flash flood setup, pavement becomes a delivery system for water. Then the rain hits soil. Soil can absorb water, but only up to a point. If the soil is already wet, if it is compacted, if it has clay content, if the rainfall rate is too intense, or if water arrives faster than it can infiltrate, the surface begins to shed water. A yard becomes a slope. A field becomes a sheet. A roadside shoulder becomes a channel. The difference between absorption and runoff can change within the same storm. This is where the atmosphere hands the event to the land. A rain band over a natural basin becomes runoff into streams. A rain band over a city becomes runoff into drainage systems. A rain band over a highway becomes runoff into lanes, shoulders, medians, underpasses, and low ramps. The water has no opinion about the human design below it. It follows gravity. The human system either gives it a safe path or becomes the path. That is the basic physics of flash flooding. Water moves downhill. It concentrates in low places. It accelerates through narrow openings. It backs up when openings are blocked or undersized. It spreads when channels exceed capacity. It hides depth when it covers pavement. It becomes more dangerous when people enter it. Arthur's rainfall risk follows that chain, from the atmosphere into roofs, from roofs into streets, from streets into drains, from drains into culverts, from culverts into creeks, from creeks into crossings, from crossings into traffic, from traffic into dispatch, from dispatch into rescue. By the time the public sees the most dramatic part, the system has already been carrying load for a while. That is why flash flooding often feels sudden even when the mechanism has been building. The atmosphere may have been moist for hours. The rain bands may have been visible on radar. The forecast may have described heavy rainfall. The flood watch may have been posted. But at ground level, the transition from inconvenience to danger can be abrupt. The water reaches a threshold. The inlet stops keeping up. The ditch fills to the road edge. The culvert backs water upstream. The underpass begins to pond. A driver rounds a curve and sees water where road should be. The mechanism becomes personal only at the last visible moment. But it is not random. There are steps. First, moisture is available. Tropical moisture increases the amount of rain a storm can produce. Second, lift turns that moisture into clouds and rainfall. Third, slow movement or training concentrates rainfall in time and space. Fourth, rainfall rate exceeds infiltration and drainage capacity. Fifth, runoff moves toward low points. Sixth, roads and small drainage structures become overwhelmed. Seventh, people encounter water in places they expected to function normally. This is the hidden architecture of the event. It is easy to focus on the sky because the sky looks like the source. But flood damage is often determined by the connection between the sky and the surface. The same rainfall rate can produce very different outcomes depending on where it lands. A rural basin with room to spread water is not the same as a paved urban corridor. A clean culvert is not the same as one blocked by branches. A maintained drainage ditch is not the same as one filled with sediment. A high road is not the same as a low crossing near a creek. The mechanism is atmospheric at the top and local at the bottom. That is what makes it hard to warn perfectly. Forecasters can identify the region where heavy rain is likely. They can see moisture, instability, boundaries, radar trends, and model signals. They can issue watches and warnings, but the exact flooded street may depend on a band shifting a few miles, a drain clogged by debris, a creek responding faster than expected, or a burst of rain arriving during traffic. The atmosphere sets the table. The local surface decides the first place where the plate falls. This is why Arthur's remnants should not be judged only by how they look on satellite. A weakening storm can still sit inside a humid environment. A disorganized system can still have rain bands. A remnant low can still interact with boundaries. A post-tropical label can still be tied to dangerous rainfall. The name can fade while the physical ingredients remain aligned. That alignment is the mechanism. Moisture is the fuel. Lift is the hand that squeezes it. Training is the conveyor. Rainfall rate is the delivery speed. Drainage capacity is the bottleneck. Human exposure is the consequence. Each piece matters. Take away moisture, and the system cannot produce as much rain. Take away lift, and the moisture remains suspended. Take away training, and the rain may spread out instead of focusing. Increase drainage capacity, and streets may stay passable longer. Reduce exposure, and fewer people meet the water at the wrong place. But when moisture, lift, training, limited drainage, and human movement overlap, the event becomes a flash flood setup. This is not just a storm moving inland. This is a moisture machine moving into a built environment, and the built environment is full of small assumptions. The road assumes water will leave. The drain assumes flow will stay within design limits. The culvert assumes debris will not choke the opening. The bridge assumes the stream will remain below the deck. The driver assumes the pavement continues beneath the water. The dispatcher assumes there are alternate routes. The hospital assumes staff and patients can still arrive. Heavy tropical rain tests those assumptions at the same time. That is the system load. A single overwhelmed drain may not sound like a disaster, but it can flood an intersection. That intersection can block a bus route. The blocked route can delay workers. A stalled car can trigger a rescue. A rescue can pull personnel away from another call. A closed road can move traffic to a second road. The second road may also flood. Now the hazard is not just water, it is cascading delay. Flash flooding is often a chain of small failures, not one giant collapse. Arthur's inland risk should be understood that way. The rain is not simply falling on empty land, it is falling on a connected system. It falls on neighborhoods where people are making decisions. It falls on road networks with low points. It falls on drainage structures with limits. It falls on emergency services with finite crews. It falls on hospitals with shift schedules. It falls on power systems where trucks need road access. It falls on local governments that have to warn, close, clear, rescue, and communicate while the event is still changing. The atmosphere starts the event. The system distributes it. This is the part that can make a weakening storm more dangerous than it appears. The visible violence declines. The operational complexity increases. Wind damage may be easier to understand because people can see trees bending, signs shaking, power lines moving. Flood risk can be harder because the most important changes begin in flow paths, drainage margins, and water levels that are not obvious until they cross a threshold. The event is visible outside. The damage begins inside the system, inside the drainage system, inside the road network, inside dispatch timing, inside household decisions, inside the body of a person who sees water ahead and has to decide whether to continue. That is where the mechanism is heading. From a weather office, it begins as moisture and lift. On radar, it becomes a band. On the ground, it becomes runoff. At the curb, it becomes a drainage problem. At the underpass, it becomes a transportation hazard. At the steering wheel, it becomes a human decision. At dispatch, it becomes a rescue call. At the hospital, it becomes access and delay. The same water changes identity as it moves. In the sky, it is precipitation. On the street, it is runoff. At the culvert, it is hydraulic load. At the road closure, it is public safety. In a stalled vehicle, it is survival. In the operations room, it is a cascading incident. This is why the mechanism matters. It prevents the story from becoming superstition. Arthur is not dangerous inland because remnants are mysterious. It is dangerous because the physics are clear. Tropical moisture plus lift can produce efficient rain. Efficient rain plus slow movement can produce high rainfall rates. High rainfall rates plus vulnerable drainage can produce flash flooding. Flash flooding plus human exposure can produce emergencies. There is no need to exaggerate it. The mechanism is enough. The warning does not say that every street will flood. It does not say every county will see the worst case. It does not say Arthur will become a historic disaster everywhere it rains. It says the ingredients are present for dangerous to life-threatening flash flooding where heavy rain concentrates. That is a narrower claim, and it is stronger because it is true. The future of this event depends on concentration. Where does the band slow down? Where does the heaviest hour land? Where are drains clogged? Where are roads low? Where is the soil already wet? Where are people driving when the burst arrives? Where does water find the first opening in the system? That is the investigation now. Not the shape of the storm, but the path of the water. Arthur's remnants are not only moving across a map, they are moving through layers: atmosphere, surface, drainage, road, vehicle, dispatcher, rescuer, hospital. Each layer changes the meaning of the same rainfall. Each layer adds delay or danger. Each layer can absorb some load until it cannot, and when one layer fails, the next layer receives the problem. That is how a rain forecast becomes a flood emergency. The mechanism begins above the gulf, but it does not end there. It travels downward until it reaches a person who has no time to read the atmosphere. For that person, the physics arrive as a flooded road, a dark windshield, a phone alert, and one decision that has to be made before the water reveals how deep it is. The next clue is not on the radar. It is inside one driver's night. The mechanism enters the world through one person before it becomes a statistic. Picture a driver in southern Alabama or western Georgia after a late shift. Not a reckless driver, not someone trying to challenge the storm, just a person doing an ordinary thing at the wrong hour in the wrong rain band. The phone has already buzzed once with a weather alert. The windshield wipers are moving fast. The headlights are catching sheets of rain. The road is familiar enough to create confidence, and that confidence is part of the danger. This is how tropical moisture becomes personal. It does not arrive as a satellite image. It does not arrive as a rainfall estimate in millimeters. It does not arrive as a phrase from a federal forecast discussion. It arrives as reduced visibility, a missed lane marking, a brake light appearing too late, and water beginning to spread across the low side of a road the driver has used many times before. The body does not experience climate change as a graph. It experiences it as a decision made in low visibility. At first, the driver may not feel trapped. The rain is heavy, but heavy rain is familiar in the southeast. The road still appears open. Other vehicles may still be moving. The storm has weakened, and that fact may sit somewhere in the back of the mind as permission to keep going. Arthur is no longer the kind of storm that sounds terrifying. The center is inland. The wind is not the main story. The danger feels downgraded, but the water does not know that. The water is moving through the mechanism already described. It has fallen out of a tropical air mass. It has run off roofs, driveways, parking lots, and compacted lawns. It has reached curbs and ditches. It has pushed towards storm drains and culverts. It has found low ground. It has begun collecting where the road dips, where the ditch narrows, where the pipe under the road is too small, or where leaves and branches slow the flow. The driver sees only the final layer, a sheet of water across pavement. That is the human pathway of a flash flood. The atmosphere does not strike the person directly. It changes the environment around the person until ordinary choices become dangerous. The rain changes visibility. The runoff changes road friction. The water changes depth perception. The current changes vehicle control. The alert changes urgency. The flooded route changes the decision tree. And all of that can happen before the person fully understands that the system around them has changed. A road is a promise. It promises continuity. It says that the pavement ahead connects to the pavement behind. It says that the lane line marks a safe path. It says that the shoulder is where the road ends, not where a hidden ditch begins. It says that headlights reveal enough information to keep moving. In normal rain, that promise usually holds. In flash flooding, the promise can fail. Water erases the evidence. It covers the line. It hides the pavement edge. It makes a shallow dip look like a shallow puddle. It hides a blocked drain, a washed shoulder, a culvert opening, a ditch, debris, or fast-moving flow below the surface. From inside the vehicle, the scene becomes flatter than it really is. The driver sees reflection, not depth, surface, not force. That is why water on a road is not just water on a road. It is missing information. The driver may slow down. They may look for the center line. They may watch another vehicle ahead and assume the route is safe if that vehicle made it through. They may think the water is only a few inches deep. They may feel pressure from a vehicle behind them. They may be tired. They may have a child waiting at home. They may need to reach a second job. They may not know another route. They may believe turning around is more dangerous than continuing. Flash flooding often enters through those ordinary pressures. It does not need panic. It needs uncertainty, fatigue, obligation, and a familiar road made unfamiliar by water. The rain outside becomes a physical load inside the vehicle. The driver grips the wheel harder. The foot hovers between brake and accelerator. The windshield wipers cannot clear the glass fast enough. The sound of rain on the roof and hood narrows attention. The phone may sound again, but reading it while driving is unsafe. The safest information may be arriving at the least usable moment. The warning exists. The body is busy surviving the road. That gap between warning and behavior is where many flood emergencies happen. It is not because people do not care, it is because the timing is cruel. A flash flood warning may describe a county. The driver is dealing with a curve. A forecast may describe rainfall rates. The driver is looking at water across a lane. A message may say, "Turn around, do not drown." The driver is calculating whether the water ahead is shallow enough to cross. The official warning operates at one scale. The human decision happens at another. Now, follow the pathway forward. If the driver enters the water and the vehicle begins to lose traction, the event changes immediately. The car is no longer just transportation. It becomes a heavy object in moving water. Tires that were designed to grip pavement are now partly separated from it. The engine may stall. The electrical system may fail. The doors may become difficult to open if water rises against them. The person inside may not know whether to stay, exit, call, wait, or move. One decision becomes a rescue problem. The driver calls emergency services. The dispatcher asks for location. But in heavy rain, location can be hard to describe. Street signs may be obscured. The driver may not know the nearest cross street. The phone signal may be weak. Water may be rising. The dispatcher has to turn fear into coordinates. Then the rescue system has to turn coordinates into access. That is the next layer. Fire rescue may be ready, but ready is not the same as close. The nearest route may be flooded. A bridge may be closed. Another call may already be active. Crews may need high water equipment. Police may need to block traffic. Public works may need to place barricades. Emergency management may need to track multiple incidents at once. What began as rainfall in a tropical air mass has now become a resource allocation problem. The storm has entered the emergency system. This is how one person becomes part of the larger story. A single stalled vehicle can slow a road. A slow road can delay others. A rescue can require multiple responders. Responders entering floodwater face their own risk. A road closure can push traffic onto secondary routes. Secondary routes may include other low spots. Calls can arrive faster than crews can clear them. The public may not yet understand the pattern because each incident looks isolated from the outside. But inside the operations room, the pattern is visible. Water on road, vehicle stranded, culvert overtopping, intersection flooded, creek rising, route blocked, another vehicle stranded. This is not one dramatic wall of water sweeping through a city. It is a network of smaller failures appearing faster than the system can absorb them. For the driver, the experience is not a network. It is immediate. The cold water at the door, the sound of rain, the uncertainty about depth, the voice on the phone asking where they are, the headlights of another vehicle stopping behind them, the fear that the water is still rising, the realization that the storm sounded weaker than this moment feels. That realization is central to Arthur's inland risk. The public herd weakening. The body receives load. A person does not need to understand precipitable water to be endangered by it. They do not need to know the term training rain band. They do not need to know how the Weather Prediction Center estimates rainfall rates. The mechanism reaches them anyway. It comes through the road surface, through the drainage system, through the timing of the trip, through the gap between what the map suggests and what the pavement is doing. This is why the human pathway matters. Without it, flash flooding can sound like a technical hazard. Rainfall rates, drainage capacity, basin response, urban runoff, hydrologic load. These are accurate words, but they do not show the moment when the hazard becomes life. The hazard becomes life when someone has to decide whether to continue forward through water that hides its own danger. That decision is shaped by systems. Was the road marked as flood-prone? Were barricades already in place? Did the phone alert arrive in time? Was the driver able to delay travel without losing income? Did the workplace close early? Did local officials communicate the specific roads at risk? Were storm drains cleared before the rain? Was there enough lighting at the low crossing? Was there an alternate route that did not add an hour? Was public transportation available? Was the person already exhausted from work? The flood enters the body through infrastructure and economics as much as through weather. This is the part that cannot be captured by a storm track. A storm track shows motion, a human pathway shows exposure. The track says the remnants are moving inland. The pathway asks who is on the road when the heaviest hour arrives. The track says the system has weakened. The pathway asks whether the driver has enough information, enough time, and enough safe options to avoid the water. Risk is not only what the atmosphere does, risk is what the atmosphere does to people who have limited choices. That is why flash flooding is so unequal in practice. Some people can stay home, others must move. Some have vehicles high enough to pass shallow water, although that can create dangerous false confidence. Others drive small cars that lose control sooner. Some live on higher ground. Others live near drainage channels, creeks, low apartment lots, or roads that pond early. Some receive alerts and understand them immediately. Others are working, sleeping, driving, caring for children, or using a phone with low battery. The same rain falls into different lives. For the driver in this story, the event may end with rescue. It may end with a soaked car and a towing bill. It may end with a closed road and a long detour. It may end safely because they turn around before the water. The outcome is not predetermined. That matters. The purpose of understanding the pathway is not to make the story hopeless. It is to see where risk can be interrupted. A warning can interrupt it. A barricade can interrupt it. A clear drain can interrupt it. A delayed shift can interrupt it. A local road closure map can interrupt it. A driver turning around can interrupt it. But each interruption has to happen before water removes the margin. That is the central tension of Arthur's flood story. The storm is not only moving across geography, it is moving through time, forecast time, warning time, travel time, response time, drainage time, rescue time, recovery time. Flash flooding becomes dangerous when those clocks stop lining up. The rainfall arrives faster than the drain can clear. The warning arrives later than the decision. The rescue arrives after the road is cut off. The storm label fades before the hazard peaks. This is not just a weakening storm. This is a drainage system failure moving through one person's night. And once it moves through one person, it does not stay there. The driver becomes a call. The call becomes a route. The route becomes a closure. The closure becomes a delay. The delay becomes a hospital staffing problem, a missed shift, a stranded family, a blocked ambulance, a power repair postponed, a grocery truck rerouted, a school decision reconsidered before morning. That is how flash flooding scales. It begins with water, where water should not be. It grows when people and systems have to respond while the rain is still falling. It becomes more than weather, when the ordinary network of movement stops behaving like a network. The human pathway is not separate from the infrastructure pathway. They are the same path seen from different positions. From the sky, it is a rain band. From the curb, it is runoff. From the driver's seat, it is a decision. From dispatch, it is a call. From public works, it is a blocked drain. From the hospital, it is a delayed arrival. From the city, it is a system test. The next part of the story is smaller than the storm and closer than the river. It is the opening where the water is supposed to disappear. The weak point is not the whole city. It is not the entire highway system. It is not every bridge, every road, every neighborhood, or every hospital. In a flash flood setup, the weak point is often much smaller. It may be a storm drain inlet at the edge of a curb. It may be a culvert under a 2-lane road. It may be a ditch that has not been cleared. It may be a pump station that needs more time than the rain is willing to give. It may be a low underpass that was never meant to receive water this fast. The weak point is the opening where water is supposed to disappear. On an ordinary day, almost no one notices it. A driver passes over it without looking. A child walks past it on the way to school. A delivery truck parks beside it. Leaves collect near it. Grass grows around it. A plastic bottle may sit against the grate. Sand and sediment may settle inside the pipe. The whole piece of infrastructure is small enough to vanish from public attention. Then the tropical rain arrives. Now that small opening becomes a test. A storm drain inlet has one job. It takes water from the street and moves it into the underground drainage system. The road is shaped to help this happen. The pavement slopes slightly. The curb guides water along the edge. The inlet waits at the low point. In a normal rain, this looks almost automatic. Water runs along the gutter, enters the drain, and disappears. That disappearance is the illusion of safety. The water has not vanished. It has only moved into a hidden system. Beneath the road, pipes carry it toward larger pipes, ditches, canals, detention basins, creeks, rivers, or pump stations. The system depends on capacity. It depends on slope. It depends on maintenance. It depends on the downstream channel not already being full. It depends on the inlet remaining open. It depends on the rain arriving within a range the system can handle. Arthur tests those assumptions. When rainfall rates climb, the inlet may still be working, but it cannot accept water fast enough. The gutter fills. The water spreads from the curb into the lane. The lane becomes shallow storage. Vehicles push wakes through it. The wake moves water toward driveways, sidewalks, storefronts, and yards. If the rain continues, the street stops behaving like transportation and starts behaving like a basin. That is not always because the drain is broken. Sometimes the drain is simply outmatched. This distinction matters. People often imagine infrastructure failure as a dramatic collapse. A bridge falls, a dam breaks, a road washes away. Those failures happen, and they are serious. But flash flooding can begin with a quieter failure. The system may remain physically intact while it loses functional capacity. The grate is still there, the pipe is still there, the road is still there, but the water is arriving faster than the system can move it away. The component has not disappeared, the margin has. That is the operational weak point in Arthur's inland flood threat. The storm does not need to destroy the drainage system to overwhelm it. It only has to push enough water through the openings fast enough that the system cannot keep up. A clogged inlet reduces capacity, a narrow culvert reduces capacity, a full ditch reduces capacity, a flat area reduces flow speed, a downstream channel already running high reduces capacity, a pump station that loses power or reaches its limit reduces capacity. Each reduction is local. Together, they become regional. A culvert is a good example because it is usually invisible until it matters. A culvert is a pipe or box structure that lets water pass under a road. Without it, every small stream or drainage ditch would cut the road. With it, traffic passes above and water passes below. On a normal day, the arrangement looks stable. The road belongs to people. The channel belongs to water. Each has its lane. Heavy rain blurs that separation. If water reaches the culvert faster than it can pass through, the upstream side begins to rise. Debris can collect at the opening. Branches, leaves, grass clippings, trash, and sediment can turn a partial blockage into a serious restriction. The water backs up, the ditch fills, the road shoulder saturates. Then water starts looking for another path. If the road is the lowest available crossing, the road becomes the path. That is when the human system meets the hydraulic system. A driver may not see the culvert. They see only water crossing the road. They may not know the upstream side is backing up. They may not know the downstream side is moving fast. They may not know whether the pavement beneath the water is still intact. The weak point is below the surface, but the decision happens above it. A low underpass works the same way. An underpass is built below surrounding ground because one route has to pass beneath another. On dry days, this is efficient. Traffic flows, rail lines and highways cross without interruption. The geometry saves space. But in heavy rain, the underpass is a bowl. Water runs toward it from ramps, side streets, shoulders, walls, and nearby pavement. Drains and pumps are supposed to keep the bowl from filling. If the rain arrives too fast, if debris blocks the drain, if the pump is overwhelmed, or if power is interrupted, the bowl begins to hold water. The danger is not only the depth, the danger is the shape of the trap. A driver entering an underpass may not see how deep the lowest point is. The road slopes downward before it rises again. Water may look shallow at the entrance and become deeper near the center. At night, reflections can hide the grade. In heavy rain, another vehicle's tail lights may create false confidence. By the time the driver realizes the bottom is flooded, turning around may be difficult. This is why a single underpass can become a system problem. Close it, and traffic reroutes. Keep it open too long, and vehicles may strand. Send responders, and they must approach through the same road network under stress. If several low points flood at once, the city does not simply lose roads, it loses options. Emergency response depends on options. Hospitals depend on options. Utility repairs depend on options. Families depend on options. Arthur's rainfall does not need to flood everything to reduce the options that matter. A pump station is another small component with large consequences. In low-lying areas, water may not drain away quickly by gravity. Pumps move water from one place to another, lifting it out of neighborhoods, underpasses, or drainage basins and sending it toward canals, rivers, or storage areas. When pumps work, most people never think about them. When they lag behind rainfall, the ground begins to reveal their limits. A pump station is a clock. It can move a certain amount of water over a certain amount of time. If rain arrives within that range, the system holds. If rain arrives faster, water accumulates. If power fails, if mechanical issues occur, if the downstream channel is too high, or if debris affects intake, the pump loses effectiveness. The problem may not begin as a broken machine. It may begin as a mismatch between rainfall rate and pumping rate. That mismatch is exactly what flash flooding exploits. The same is true for roadside ditches. A ditch can look crude compared with underground pipes, but it is often one of the most important drainage structures in rural and suburban areas. It carries runoff away from pavement. It gives water a place to move. It protects the road base. It connects small flows to larger channels. But a ditch only works if it has space, slope, and a clear path. When a ditch fills, the road becomes the next channel. That is the moment when a familiar shoulder changes identity. A driver may think the water is along the edge of the road, not realizing that the ditch is full and the flow is beginning to cross the pavement. The road may still look continuous, but the water is starting to behave as if the road is part of the drainage network. That is a different kind of danger. It is not water beside the road anymore. It is water using the road. This is not just a weakening storm. This is a drainage system failure. The phrase sounds large, but the failure begins small. One inlet cannot keep up. One culvert backs up. One ditch overtops. One underpass fills. One pump reaches its limit. One road closure forces traffic elsewhere. Then another component faces more load because people and water are both being rerouted. Systems fail through connections. A flooded intersection does not stay only an intersection problem. It can block an ambulance route. It can delay a nurse going to a hospital shift. It can prevent a power crew from reaching a downed line. It can slow a grocery delivery. It can strand a bus. It can force police to place barricades while other calls continue. It can send traffic into a neighborhood street that was never meant to carry that volume. If that neighborhood street has its own low spot, the problem repeats. The weak point spreads by consequence. This is why maintenance becomes part of disaster risk. Clearing drains before heavy rain is not cosmetic. Cutting vegetation from ditches is not cosmetic. Removing debris from culverts is not cosmetic. Testing pumps is not cosmetic. Updating flood-prone road lists is not cosmetic. These actions determine how much time the system has before rainfall becomes roadway flooding. Time is the hidden reserve. Every open drain buys time. Every cleared ditch buys time. Every working pump buys time. Every barricade placed early buys time. Every local warning that names specific roads buys time. The goal is not to defeat all water. No city can promise that under extreme rainfall. The goal is to keep water from surprising people faster than the system can respond. Arthur compresses that time. The official forecast gives the region warning, but the water acts locally. The first failure may occur at a place that has flooded before, or it may occur at a place where recent debris, construction, soil saturation, or rainfall concentration changes the outcome. A national map cannot show every blocked grate. A radar image cannot show every culvert. A rainfall forecast cannot know which driver will meet which crossing at which minute. That uncertainty is not a reason to ignore the warning. It is the reason to take it seriously. The public often asks whether the storm will be bad in their area. The better question is whether their area contains small places where water has nowhere safe to go. A low driveway entrance, a creek crossing, a drainage ditch behind an apartment complex, a road beneath a rail bridge, a shopping center parking lot that slopes toward the street, a neighborhood pond already high before the storm, a culvert that clogs in ordinary thunderstorms. These places are the real map. They are not always colored on national television graphics, but local responders know them. Public works crews know them. Long-time residents know them. Tow truck drivers know them. School bus drivers know them. Emergency dispatchers learn them through repetition. During a tropical rain event, those known places become early indicators. If the first ones flood quickly, the system is losing margin faster than expected. That is the warning inside the warning. Flood watches and warnings tell people the atmosphere and ground may align for danger. But the local weak points tell officials where that danger may first become visible. When those points begin to fail, the event becomes operational. Roads close, calls stack, crews move, barricades go out. Social media fills with images of water over pavement. Some of those images help, some mislead, some arrive too late for the people already driving. The system begins to chase the water, and water has advantages. It does not need permission, it does not follow road signs, it does not respect jurisdiction lines, it crosses from one property to another, it moves from city drains into county channels, it backs up from a creek into a neighborhood, it flows from a parking lot onto a state road. It enters the lowest doorway first. It finds the small mistakes in maintenance, design, and timing. The weak point is where those mistakes become physical. A storm drain covered by leaves may seem minor until a 2-inch-per-hour rain band arrives. A culvert partly blocked by branches may seem minor until upstream water rises over a rural road. A pump station with limited capacity may seem adequate until a tropical moisture plume trains over the basin. A low underpass may seem manageable until water accumulates faster than police can close it. The event does not begin as catastrophe. It begins as a question of capacity. How much water can this opening accept? How fast can this ditch move flow? How much storage remains in this basin? How quickly can crews reach the flooded point? How many alternate routes remain? How many calls can dispatch handle at once? How many rescues can be performed safely while the rain continues? Arthur forces those questions into the same window. That is the definition of system stress. Not one failure, many small demands arriving together. A storm drain has to work while a road department is placing barricades. A pump station has to work while power crews are monitoring outages. A hospital has to function while staff are delayed. A dispatcher has to answer calls while new warnings are issued. A driver has to decide while rain reduces visibility. A county has to communicate while the hazard is changing faster than the public map. This is why the weak point cannot be understood only as a piece of concrete or metal. It is also a timing point. If the drain fails before the road closes, people drive into water. If the road closes before people enter, the hazard is reduced. If a pump lags before traffic is rerouted, access is lost. If public works clears the inlet before the heaviest band arrives, the same rainfall may produce less damage. The physical component matters, but the timing around it can decide the outcome. The difference between inconvenience and emergency can be 1 hour. That is why the hidden rainfall rate from the previous section leads directly here. 1 to 2 inches per hour is not just a meteorological detail. It is a test of inlets, culverts, ditches, pumps, and low roads. The rate decides whether the system receives water as a manageable flow or as a surge of workload. The rate decides whether drainage is a service or a bottleneck. When the bottleneck appears, people see flooding, but the failure began earlier. It began when water reached the opening faster than the opening could pass it through. It began when the design assumption met a new load. It began when a storm that sounded weaker still carried enough moisture to expose the smallest parts of the system. That is the story Arthur is telling inland. A named storm can lose its name. A city can keep its roads. A drain can remain intact. And still, the system can fail at the exact point where water was supposed to leave the human world. History has already shown what happens when weak wind hides strong water. This is not speculation. A version of this mechanism has already left evidence behind. The evidence has a name that many people along the Gulf Coast still recognize. Allison. Tropical Storm Allison, in June of 2001, was not remembered because it was a major hurricane. It was remembered because weak wind hid strong water. It was remembered because a tropical system without the headline power of a catastrophic windstorm still produced catastrophic flooding. That is why Allison matters in Arthur's story. Not because Arthur is Allison, not because the same outcome is guaranteed, not because every weakening storm becomes a historic disaster. That would be the wrong lesson, and it would turn evidence into exaggeration. Allison matters because it proves the mechanism is real. Tropical moisture can outlive public attention. Rainfall can become the main hazard after the wind story fades. A storm can be physically weaker than people fear and hydrologically stronger than people expect. The lesson is not that every weak storm becomes Allison. The lesson is that weak wind can hide strong water. According to the National Weather Service assessment of Tropical Storm Allison, the worst impacts struck southeast Texas and southern Louisiana. NOAA records show extraordinary rainfall totals, including 36.99 inches at the Port of Houston and 29.86 inches at Thibodaux, Louisiana. The official assessment documented more than $5 billion in damage across the hardest-hit areas and 24 fatalities in southeast Texas and southern Louisiana. Those numbers are not being used here to frighten the viewer. They are being used to draw a line from mechanism to consequence. Allison showed that the danger of a tropical system cannot be measured only by its wind speed. The storm became a disaster through water, time, terrain, urban exposure, and drainage failure. It moved slowly. It produced repeated heavy rain. It struck a region with dense development, large paved surfaces, bayous, roads, underpasses, homes, hospitals, and people trying to move through a changing flood environment. The sky delivered water. The city had to route it. And when the routing failed, the disaster expanded. In Houston, the problem was not simply that rain fell. Rain falls often in Houston. The problem was that tropical rainfall kept arriving in volumes and bursts that overwhelmed the systems built to move water away. Bayous rose, streets filled, underpasses became traps, hospitals were affected, homes flooded, vehicles stranded. The city did not experience Allison only as weather. It experienced Allison as access failure, drainage failure, transportation failure, hospital disruption, and emergency response overload. That is why it belongs in this script. Arthur's current inland flood threat lives in the same category of risk, even if it is not the same scale of event. The category is not wind. It is water moving through a built environment faster than people and infrastructure can respond. The comparison has to be handled carefully. Arthur is not being described as another Allison. The available forecast and observed conditions do not justify that kind of claim. Allison was a historic flood disaster, with extreme totals, repeated rainfall, and devastating consequences. Arthur's forecast numbers and evolving setup must be judged on their own evidence. A precedent is not a prediction. A precedent is a warning about what the mechanism is capable of when the ingredients align. That is the evidence boundary. But once that boundary is drawn, the precedent becomes powerful. Allison reminds us that tropical cyclone categories are not flood categories. A named storm can be weak and still produce serious flooding. A remnant system can keep generating rainfall. A storm can lose the public's attention while gaining hydrologic impact. The danger can shift from coastal wind to inland water without a clean emotional transition for the people in its path. People understand landfall. They understand a hurricane eye. They understand wind damage. But inland flood risk is harder to visualize because it is distributed. It appears in 1,000 small places: a street, a culvert, a bayou, a drainage ditch, a hospital entrance, a freeway underpass, a neighborhood that sits lower than the roads around it, a vehicle that stalls where the driver thought the water was shallow. Allison turned that distributed risk into a historic event. Arthur does not need to become historic to prove the same kind of risk exists. It only has to place enough water in the wrong places fast enough. That is the connection. In both cases, the central hazard is water, after the easy headline weakens. In both cases, the word tropical does not only mean wind, it means deep moisture. In both cases, rainfall rate matters as much as total rainfall. In both cases, drainage systems become part of the storm. In both cases, roads become dangerous, not because they were designed to be rivers, but because water forces them into that role. The map shows weather, the flood reveals design. Allison also showed something that is easy to forget until the next event. Recovery from floodwater is not immediate when the rain stops. Water leaves damage behind in layers. Cars do not restart because the warning expires. Homes do not dry because the storm has moved on. Hospitals do not regain normal access instantly if surrounding streets are damaged or blocked. Roadbeds may be weakened. Electrical systems may be compromised. Mold begins later. Insurance claims begin later. Missed work begins later. Medical stress begins later. The storm can pass before the consequences finish arriving. That is why flash flooding is not only a moment of water, it is a chain of recovery. Allison made that chain visible. Arthur is testing whether the lesson has been absorbed. Do people still relax when the wind number falls? Do they still treat remnants as leftovers rather than active hazards? Do they still think inland counties are outside the main story? Do they still use the storm track as a substitute for the rainfall map? Do they still wait to see water before changing behavior? Those questions matter because the physical mechanism has not changed in the way public attention often changes. Moisture still moves inland, rain bands still train, pavement still accelerates runoff, culverts still clog, low roads still fill, vehicles still lose control in water, rescue systems still have limited capacity, hospitals still depend on access roads. Warnings still have to cross the distance between official language and personal action. Allison is the evidence that this chain can break badly, but the comparison also shows what is different. Arthur's rainfall forecast is serious, but the forecast does not automatically equal Allison's extreme totals. Arthur's track, speed, rainfall placement, soil conditions, and local vulnerabilities are specific to this event. The storm may produce damaging flash flooding in some places and less severe impacts in others. Some counties may experience heavy rain without catastrophic outcomes. Some drainage systems may hold. Some roads may be closed early enough. Some people may turn around in time. That matters. A good warning does not need every worst case to happen. It needs people to understand why the risk is real before the worst case has a chance. The goal is not fear. The goal is recognition. Allison teaches recognition. It teaches that a tropical storm does not need to be visually impressive to be dangerous. It teaches that water can become the dominant hazard long after wind has stopped being the headline. It teaches that urban drainage is not a background service during extreme rain. It is the battlefield. It teaches that road networks are part of flood risk. It teaches that hospitals, power repair, emergency response, and ordinary commuting are connected to rainfall rates. Most importantly, it teaches that the first mistake is often mental. People downgrade the event too quickly. They hear weakening, they hear remnants, they hear no longer tropical, they hear not a hurricane, they hear inland. Each phrase can be technically true and emotionally misleading. The atmosphere may still be loaded, the ground may still be vulnerable, the drainage system may still be close to capacity, the heaviest rain may still be ahead for someone down the line. Arthur's danger sits inside that mental gap. Officially, the storm can be weaker. Operationally, the flood risk can still be rising. This is the same kind of gap Allison exposed. There is another lesson in the Allison record. Fatalities in flood events often concentrate around movement. People inside vehicles, people trying to cross water, people attempting to move through an environment that changed faster than the mind accepted. That does not make those people foolish. It means the hazard attacks a basic assumption. Roads are supposed to connect. When they suddenly do not, the consequences can be deadly. This is why the previous section focused on one driver. History turns that individual moment into a pattern. One person sees water on a road, another person sees the same. A third person meets a flooded underpass, a fourth finds a detour blocked. Dispatch begins receiving calls. Road crews begin closing locations. Social media begins filling with images. Emergency managers begin seeing clusters. The story moves from isolated decisions to system behavior. Allison showed that clustering can become overwhelming. Arthur is a smaller question with the same structure. Where will clusters appear? Which roads will flood first? Which drainage components will lose capacity? Which communities will receive the heaviest hour? Which warnings will be understood? Which people will still be traveling when the rain peaks? Which systems will have enough time to recover before the next band arrives? That is not a prediction of disaster. It is an operational framework. Past floods do not tell us exactly what Arthur will do. They tell us what to watch. They tell us not to stop watching when the storm weakens. They tell us that rain totals must be read with drainage capacity. They tell us that hourly rates matter. They tell us that roads are part of the hazard. They tell us that the most dangerous places may be small, familiar, and low. Allison is not a ghost story. It is a systems report written in water, and that is why it changes the way Arthur should be read. Arthur moving inland is not simply a storm track event. It is a test of whether the public, the forecast system, and local infrastructure can keep attention on the hazard after the dramatic part of the storm has faded. The storm name is not the only signal. The water is the signal. The drain is the signal. The flooded road is the signal. The delayed ambulance is the signal. The closed underpass is the signal. The rescue call is the signal. The historical precedent says these signals can connect. They may connect at small scale. They may connect at larger scale. The outcome depends on rainfall placement, timing, infrastructure condition, warnings, and human choices. But the connection itself is no longer theoretical. It has happened before. That is the power of precedent. It does not announce that history will repeat exactly. It shows the path history used when it broke through before. For Arthur, that path begins with a weakening storm and continues with water. It moves through tropical moisture, heavy rainfall, drainage capacity, roads, drivers, emergency response, and recovery. Allison showed that this pathway can produce consequences far beyond what the wind number suggests. Once that lesson is absorbed, Arthur stops being only a storm. It becomes part of a larger pattern. Arthur becomes a pattern when the storm label stops being the best guide to the danger. That is the shift. For generations, people have been trained to watch tropical systems through a few familiar signals. The name, the category, the cone, the landfall point, the maximum wind speed, the moment when the center crosses the coast. Those signals matter. They save lives. They tell people when wind, surge, and coastal impact may become dangerous. But they do not tell the whole story of inland flooding. Arthur exposes the gap. The official tropical story says the system weakened. The hydrologic story says the water risk continued. The public story may begin to fade when the storm loses tropical cyclone status. The operational story may become more complicated at that exact moment because the hazard has moved from a named storm into drainage networks, roads, rivers, emergency response, and recovery time. This is not only Arthur. This is a compound inland risk pattern. The pattern begins when a tropical system pulls moisture inland. It continues when the storm's wind structure weakens faster than its rainfall threat. It becomes dangerous when people use the weakening wind signal as a proxy for all danger. Then it expands when heavy rain reaches systems that were not built around the assumption that water would arrive this quickly, this widely, or this late in the emotional life of the storm. The storm is fading. The system is still loading. That is the calendar failure inside the event. A storm calendar is supposed to feel simple. Preparation before landfall, impact during landfall, cleanup after landfall. But inland flooding does not always obey that calendar. The heaviest rain can arrive after the storm is no longer at peak strength. Rivers can rise after the rain has moved on. Roads can close after the public has already decided the worst is over. Recovery can begin in one county while another county is just entering its most dangerous hour. Arthur is testing that old calendar. It is showing that the event does not end when the tropical label weakens. It ends only when the water has moved through the system, and that may take longer than the headline cycle allows. The old calendar was built around the visible storm. The new risk is built around the hidden load. That load is moisture, rainfall rate, soil saturation, drainage capacity, road exposure, river response, human movement, emergency crew availability, hospital access, utility repair routes, local communication, recovery time before the next band arrives. Each factor can be manageable alone. Together, they become a compound risk. Compound risk means the hazard is not one thing. It is several pressures overlapping. Rain falls while people are driving. Drains clog while more rain is arriving. Roads close while emergency calls increase. Hospitals remain open but become harder to reach. Power crews may be ready but lose access to damaged locations. Families may receive warnings but still face work, care, fuel, food, and travel obligations. The event becomes more than meteorology because every system has to respond at the same time. This is why the phrase weakening storm can be dangerous if it becomes the whole message. A storm can weaken in one dimension and intensify in another dimension of consequence. Wind may weaken while rainfall continues. The center may become disorganized while rain bands remain efficient. The name may fade while the hydrologic footprint expands. The satellite image may look less threatening while the ground becomes more stressed. The emergency may move from coastal evacuation to inland road closure, from hurricane preparation to flood rescue, from storm shelters to drainage crews and dispatch centers. That is the system pattern Arthur reveals. Not a single catastrophic claim, a shift in how risk travels. The first system being tested is public attention. Attention is a limited resource. During a named storm, attention is high. People check forecasts. Officials hold briefings. News outlets show maps. Families talk about supplies. When the storm weakens, attention often drops. That drop can be rational if the hazard truly drops, but it becomes dangerous when one hazard declines while another remains. Arthur's warning sits inside that conflict. The tropical cyclone signal weakens, the flash flood signal remains. The public hears one kind of relief. Forecasters are still describing another kind of danger. The risk is not that people are unintelligent. The risk is that the communication system has trained them to prioritize the most visible storm metric. Wind is easy to symbolize. Water is harder. A category turns wind into a simple scale. A cone turns track uncertainty into a familiar graphic. A landfall point gives the mind a target. But flood risk spreads through basins, pavement, soil, drainage channels, and time. It does not fit neatly into one number. It can be severe outside the center. It can peak after landfall. It can strike a neighborhood that did not feel central to the storm track. So the first new baseline is mental. People need to read tropical systems not only from the top down, from the storm center to the map, but from the bottom up. From the lowest road and the smallest drain back to the rainfall field, the second system being tested is infrastructure. Much of the built environment was designed around assumptions. How much rain falls in a typical storm? How often extreme rainfall occurs? How quickly water moves across a basin? How much runoff pavement creates? How long pumps need to operate? Where creeks usually stay within banks? Which roads usually remain passable? Which neighborhoods flood first? Which channels have enough capacity? Those assumptions may still work most days. They are not useless, but extreme rainfall tests them at the edge. And when the edge is reached more often, the old assumption becomes a weak foundation. Arthur does not need to be a record-breaking disaster to expose that. A moderate flood event can reveal the same structural questions. Which drains clog first? Which low roads fill first? Which pump stations fall behind first? Which communities depend on one access route? Which hospital corridors have flood-prone approaches? Which emergency plans assume roads will remain open longer than they actually do? That is how a storm becomes an audit. It audits the drainage map. It audits maintenance. It audits communication. It audits road closure protocols. It audits whether people know alternate routes. It audits whether vulnerable residents can avoid travel. It audits whether local officials have enough barricades, crews, and real-time information to keep water from becoming a surprise. The event is weather. The pattern is governance under rainfall stress. The third system being tested is recovery. Recovery is often imagined as something that begins after the hazard ends. But in flood events, recovery can start while danger is still ongoing. One road may need clearing while another is flooding. One neighborhood may begin pumping water while another is receiving a new rain band. One county may be assessing damage while downstream communities are waiting for creeks and rivers to rise. This creates a recovery overlap. The system has to respond, repair, communicate, and prepare for the next wave at the same time. That overlap is becoming more important. Tropical moisture events do not always arrive as a single clean impact. They can come in rounds. A first band saturates soil. A second band overwhelms drainage. A third band pushes streams higher. After that, even lighter rain can create problems because the system has lost capacity. The danger is not only the peak rainfall, it is the lack of recovery time between loads. The future will not be decided only by the peak number. It will be decided by whether the system has time to recover before the next load arrives. Arthur's rainfall forecast carries that lesson. 5 to 10 inches is not only a total, it is a demand placed across time. If the rain arrives slowly and the system has space, some places may handle it. If heavy bands repeat, the available recovery time shrinks. If drains are already carrying water when the next burst arrives, the second burst does not start from zero. If creeks are already elevated, the next inch has a different meaning than the first. The baseline changes during the event. That is hard for the public to see because the landscape may look only wet, not failing. A street with water at the curb may still function. A creek near bankfall may still look contained. A ditch carrying fast water may still be beside the road, but those are not neutral conditions. They are reduced margin. The system is closer to failure even before the dramatic image appears. Arthur's pattern is about margin. How much drainage margin remains, how much road access margin remains, how much emergency response margin remains, how much public attention margin remains, how much recovery margin remains. When margins shrink together, small failures connect. A low road closes, traffic shifts, a second road clogs, an ambulance reroutes, a hospital staff change is delayed, a drainage crew cannot reach an inlet, a stranded vehicle becomes a rescue. A rescue crew is no longer available for the next call. The event scales not because every place floods catastrophically, but because many places lose just enough capacity at the same time. This is compound risk in plain language. Enough things are stressed together that the system has fewer ways to absorb the next problem. The fourth system being tested is the information chain. Federal agencies can issue accurate forecasts. Local offices can issue warnings. Emergency managers can post alerts. News outlets can repeat safety language. But the information still has to become a changed decision. Do not drive through flooded roads. Avoid low crossings. Delay travel if possible. Move vehicles from flood-prone spots. Check local road closures. Understand that weakening wind does not cancel flood danger. The information chain is only successful if it reaches the right person before the wrong road. That is not a simple task. People are sleeping, driving, working, caring for children, using phones with low battery, living in places with language barriers, moving through areas where road signs are poor, depending on jobs that do not close easily. Trying to interpret warnings that describe counties when their decision is at one intersection. The pattern is not only atmospheric, it is social. A rainfall rate becomes a disaster risk partly through exposure. Who has to move? Who can stay home? Who lives near low ground? Who has insurance? Who has a reliable vehicle? Who receives alerts? Who trusts them? Who has another route? Who can afford to miss work? Who can replace a flooded car? Who can recover after the water leaves? This is where Arthur's story widens beyond one storm. Flood risk is not distributed only by the clouds. It is distributed by housing, roads, work schedules, infrastructure investment, health access, and emergency capacity. Two families under the same rain band may face very different danger because one has higher ground, flexible work, a garage, and multiple routes, while the other has a low apartment lot, one vehicle, an hourly shift, and a road that floods early. The weather is shared. The vulnerability is not. That does not mean the forecast should become political theatre. It means a serious operational analysis cannot stop at rainfall totals. It must ask how water moves through unequal systems. If the low road serves a hospital, the flood is not only local. If the flooded neighbourhood has many elderly residents, the risk is not only water depth. If the main access route serves workers on night shift, timing matters. If school buses use rural crossings, morning decisions matter. If emergency crews depend on the same roads that flood first, planning matters. The pattern is physical and human at the same time. The fifth system being tested is climate memory. Not every event can be assigned to climate change in a simple, direct sentence. That is not how evidence works. One storm has ingredients, dynamics, timing, and local conditions. But the broader context matters. A warmer atmosphere can hold more water vapor. Heavier rainfall events are a major concern in a warming climate. Urban expansion adds more hard surfaces. More people and assets sit in flood-exposed areas. Drainage systems designed around historical rainfall may face events that strain their assumptions. This does not mean every flooded street has one cause. It means the baseline for water risk is changing. Arthur fits into that larger question as a warning about categories. The future may not only bring storms that are stronger at the coast. It may bring more situations where the most serious damage is inland, where the storm category does not express the flood risk, where remnants remain dangerous, where rainfall rates overwhelm infrastructure, and where recovery time becomes the scarce resource. The future storm may not look more dramatic. It may simply deliver water in a way the old system cannot route. That is the new baseline to watch. Not only peak wind, not only landfall, not only the cone. Watch the moisture plume. Watch the rainfall rate. Watch training bands. Watch saturated soils. Watch low crossings. Watch small creeks. Watch storm drains. Watch underpasses. Watch the roads to hospitals. Watch the time between bursts. Watch whether people are being told not only that rain is coming, but which systems may fail first. Arthur is a case study in that shift. The event begins with an official signal that seems to reduce fear, no longer a tropical cyclone. But the next official signal says the water remains dangerous. That is the exact pattern future risk communication must handle better. The message cannot rely on the storm name to carry public attention. It has to carry the hazard itself. The storm label is not the hazard. The water is the hazard. The drainage load is the hazard. The blocked road is the hazard. The timing is the hazard. The old preparation calendar asks when the storm arrives. The new pattern asks when the water reaches the weak point. The old map asks where the center goes. The new pattern asks where the heaviest hour lands. The old recovery plan asks when the wind drops. The new pattern asks whether roads, drains, crews, hospitals, and households have recovered before the next load. This is not only a flood story, it is an infrastructure test. It is a communication test. It is a recovery test. It is a test of whether public attention can follow danger after the dramatic label fades. Arthur will pass. The rain shield will move. Watches and warnings will eventually expire. Crews will remove barricades. Roads will reopen. Water will drain from some places and leave damage in others. The event will become a record, then a memory, then a reference point. The next time a weakening storm moves inland with a moisture field still attached, but the pattern will remain. A system built around old storm assumptions is being tested by water that does not care when the name fades. That is why the final step is not to exaggerate Arthur. The final step is to draw the evidence line clearly before the future echo begins. The final step is not to make Arthur larger than the evidence. The final step is to see what the evidence already says. The warning does not need exaggeration. The evidence is already enough. According to the National Hurricane Center, Arthur weakened and was no longer a tropical cyclone. That is true. According to the same official signal, heavy rainfall tied to Arthur's remnants remained a serious inland hazard. That is also true. Federal forecasters still describe the possibility of dangerous to life-threatening flash flooding. The Weather Prediction Center continued to track heavy rain associated with the remnants after the tropical label had faded. Those facts can stand on their own. Arthur does not have to be called a historic disaster before it deserves attention. It does not have to become another Allison before the warning matters. It does not have to produce the worst possible rainfall total everywhere for the risk to be real somewhere. Flash flooding is not judged only by the broadest map. It is judged by the place where water arrives too fast for the local system to move it away. That is the evidence line. What is clearly related is the rainfall. Tropical moisture tied to Arthur's remnants is part of the inland flood threat. The official forecast connects the remnants with heavy rain. The rainfall forecast connects the storm to drainage stress. The rainfall rate connects the atmosphere to flash flooding. The road network, the storm drains, the culverts, the underpasses, and the emergency response system are the pathways through which that rainfall becomes consequence. What is also clearly related is timing. A storm weakening in wind does not automatically mean a flood threat is weakening at the same pace. A tropical label can fade before water finishes moving through the landscape. The center can become less important while rain bands remain dangerous. Public attention can decline while drainage load increases. That mismatch is central to Arthur's story. What is only coincident must be treated carefully. Not every flooded street in the region can automatically be assigned to Arthur without local evidence. Not every traffic delay is proof of flood impact. Not every power issue, hospital strain, or emergency call has the same cause. Weather can overlap with maintenance problems, construction, old drainage issues, saturated soil from earlier rain, local creek behavior, and human decisions. A serious analysis does not force every problem into one explanation. The evidence is stronger when it does not pretend to know more than it knows. What is not yet proven must stay outside the line. It would be wrong to say that every impact from Arthur was caused by climate change in a simple, direct way. It would be wrong to say that Arthur proves all future storms will behave exactly like this. It would be wrong to say that a weakening tropical system will always create catastrophic inland flooding. It would be wrong to say that one forecast number guarantees one outcome for every community under the rain shield. That kind of certainty is not science, it is performance. The better claim is narrower and more powerful. Arthur shows how a weakening storm can still carry a serious water hazard inland. Arthur shows how the public meaning of a storm can change faster than the physical risk. Arthur shows how rainfall totals and rainfall rates must be translated into drainage capacity, road exposure, emergency response, and human decisions. Arthur shows why the most dangerous part of a storm may not be the part with the strongest name. That is enough. The danger is not imaginary. The boundary is not vague. The official signals point in the same direction. A storm lost tropical status. Heavy rain remained. Flash flood risk remained. Water continued moving through systems that can fail at small points. That is the story. This is not just a weakening storm. This is a drainage system failure. But even that sentence needs to be understood correctly. It does not mean every drain fails. It does not mean every city collapses. It does not mean the whole region is helpless. It means the real test is not only in the atmosphere, it is at the places where water meets design, the curb inlet, The culvert, the ditch, the pump, the low road, the underpass, the hospital access route, the rescue path, the driver's decision. That is where the forecast becomes operational, and that is where the ending begins. Return to the first signal. The National Hurricane Center says Arthur is no longer a tropical cyclone. In another kind of story, that would sound like relief. The storm has weakened. The name has lost force. The visible threat has faded. The public mind begins to move on. But the same signal says water is still coming. That is the contradiction this whole story has followed. The storm can shrink in one category while expanding in consequence. The wind can lose the headline while the rain keeps writing the damage. The official label can change while the ground still has to absorb, root, pump, drain, and survive the load. The map shows a fading storm. The system receives water. That is why this event should change the way Arthur is remembered. Not as the strongest storm, not as the most dramatic storm, not as a storm defined by wind. Arthur should be remembered as a warning about attention. It shows how danger can move into a quieter phase at the exact moment people begin to stop watching. The eye is not the only story. The cone is not the only map. The category is not the only warning. The question is not only where the center goes. The question is where the water goes after the center stops being the center of attention. That question leads downward. It leads to the lowest street in a neighborhood. It leads to the culvert under a rural road. It leads to the underpass beneath a highway. It leads to the ditch behind an apartment complex. It leads to the storm drain covered by leaves. It leads to the road a nurse uses to reach a hospital. It leads to the route an ambulance needs when minutes matter. It leads to the driver who sees water ahead and has to decide before the water reveals its depth. That is where future storms will be judged, not only by their peak wind, but by how long their water remains dangerous, not only by their landfall, but by where their rain bands train, not only by their name, but by whether the systems below them have margin, not only by the forecast map, but by whether people understand the hazard before the road disappears. Arthur will pass. The rain will move. The advisories will end. Watches and warnings will expire. Road crews will remove barricades from places that are safe again. Some streets will dry quickly. Some ditches will keep carrying water. Some creeks may stay elevated after the sky has cleared. Some cars may be towed. Some homes may need cleanup. Some families may remember the night, not as a named storm, but as the moment a normal road stopped being normal. That memory matters because the next storm will not arrive as a blank event. It will arrive into a world that has already been warned. The future will not be decided only by the largest number in the forecast. It will be decided by whether the hidden number is understood in time, the hourly rainfall rate, the drainage margin, the recovery window, the distance between a warning and a decision, the small opening where water is supposed to disappear. Those are the numbers that decide whether a storm becomes a manageable event or a cascading emergency. The future will also be decided by whether systems learn. Does the city clear the drains before the next tropical plume? Does the county mark the low crossings more clearly? Does the hospital plan alternate access routes? Does the road department close the underpass before the first car stalls? Does the forecast message say not only that rain is possible, but that the storm weakening does not end the flood threat? Do people learn to read remnants as active hazards when water is still attached to them? That is not despair, that is responsibility. There is a difference between fear and readiness. Fear watches the storm name. Readiness watches the water. Fear waits for the worst image. Readiness identifies the weak point before it fails. Fear treats a weakening storm as finished. Readiness asks what hazard remains after the label changes. Arthur is not asking people to panic. Arthur is asking them to update the map in their heads. A storm map is not complete if it stops at the center. A risk map is not complete if it ignores the road. A warning is not complete if it tells people the storm is weaker without making clear that the water can still be dangerous. A recovery plan is not complete if it assumes the event ends when the advisory ends. The event ends later. It ends when the water has moved through the system, through the clouds, through the streets, through the drains, through the creeks, through the road closures, through the rescue calls, through the hospital access routes, through the cleanup, through the household bills, through the memory of the people who saw the road disappear under rain from a storm that had already been described as weaker. That is the future echo. The next time a tropical system moves inland and loses its name, the question should not be whether the story is over. The question should be, what part of the story is being handed off? From hurricane forecasters to rainfall forecasters, from wind maps to flood maps, from coastal alerts to inland road closures, from atmospheric structure to drainage capacity, from public attention to local action. The handoff is the dangerous moment. Arthur's signal is clear because it sits at that handoff. The storm was no longer the same kind of storm. The water was still the same kind of threat. The label had changed. The load had not disappeared. That is what this video has been tracing from the start. Official signal, headline number, hidden rate, moisture mechanism, human decision, drainage weak point, historical precedent, system pattern, evidence line, future echo. The story began with an advisory that sounded like decline. It ends with a question about design. How many systems are still built around the assumption that the most dangerous part of a storm will be the part with the strongest name? Arthur suggests the answer may be too many. The event will pass, but the thing it revealed will remain. A system built around old storm assumptions is being tested by water that does not stop when the name fades. The next storm may look weaker on the map. The next warning may sound less dramatic. The next remnant low may not hold public attention, but the water will still look for the lowest place. It will still test the drain. It will still find the underpass. It will still reach the driver before the final report is written, and the future will be decided there, not at the center of the storm, but at the small opening where the water was supposed to disappear. Trò chuyện thoại đã kết thúc.